All right, welcome to the webinar today about parameters to measure in ultrasonic transducer impedance analysis. This is a really important topic for ultrasonic transducers to be able to measure these properties correctly, to understand what they mean, and yeah, make use of this, make more use. If you're already using this technique, make more use of it, have a better understanding about what you're measuring and why, or if you're missing something. And if you're not using it, you'll gain an appreciation of why you might want to use it, and then implement that and gain the benefits, because it's all about what the data can tell you, not just simply taking the data or just because it's the standard thing to do, you just do it. So I'm going to be speaking about what impedance analysis actually is, very generally what instruments are used to measure it. That's not the topic in detail today, but today I'm going to be going over specifically how impedance is measured, super quick overview of all the measured parameters. Probably you guys know what anti-resonance is. It's the it's the maximum impedance, and I'm not going to be dwelling too much on that part, but I will be talking in detail about what considerations you need to make in order to make that measurement correctly. And I'll be going into specific transducers, and I'll be measuring them live, and I'll be talking through how I measure these transducers. The ultrasonic Langevin transducer, which is going to be, I'll just actually show it just for better representation here. 1, 2, 3, here we go. We got this one, ultrasonic resonance, and we have this piezo disc, so I'll be showing how to measure a disc, and also this bending transducer, which is a different beast altogether about what's going on there. So I'll be doing those three measurements. I'm sure you guys are going to find it very useful going forward. So all right, so before we get into that, I have a just a kind of introduction to my company, Ultrasonic Advisors. I provide ultrasonic transducer consulting on several different types of devices. I've mainly focused on bolt clamped Langevin transducers, but also I provide expert help for a whole bunch of different devices and transducer technologies. I focus on providing finite element simulation help, and also a whole bunch of other services, including advisory services. But I've found actually that this finite element analysis using COMSOL has really helped my clients and given them the most results in combination with my advisory services. I feel like as a contractor and as a consultant, I can provide my clients the most help because they're mainly, in charge of the hands-on work, and that's usually how it mostly goes. So let's talk about, well, how is impedance measured, or what exactly is impedance? And I'm going to be going over this very quickly. I assume most people know what it is. What is impedance? But just for reference, impedance, it's defined, it's almost like resistance for the AC case. So everybody's familiar with resistance, a resistor, but it's like a resistor for an AC case. It's denoted by Z. And because it's a AC measurement, it also has a phase angle associated with it. So we have, if you excite a given device, let's say let's call it a block. If you give it a sine voltage, and this is just a block of this random device under test. If you excite it with some AC current, AC voltage, you will get then an AC current response. Hopefully at the same frequency, that means it's linear. So you'll get a certain current amplitude, you'll get a certain voltage amplitude. In between voltage and current, there's going to be a phase. So voltage amplitude divided by the current amplitude, that is the impedance. So you could also represent it as admittance. That's all right. But basically this is impedance, and its quality comes from the electrical and mechanical response of the transducer, because piezoelectric transducers are electromechanical. Therefore, their mechanical behavior then contributes toward their electrical response. And that's what we're kind of mostly interested in when we're measuring impedance. We're not interested in per se just the electrical part. We're mostly interested in what the electrical part means for the mechanical response. So how do you measure the impedance response? Basically, there's a couple of devices. There's the LCR meter. There is what's called the impedance analyzer. Oh, that makes sense. Analyzer. There's also the network analyzer, or you can just use a good old, oscilloscope, voltage, voltage probe and current probe. And that's actually what I'm going to be doing today. I'm going to be showing a live demonstration of that, but it's all automated, so you won't be able to tell the difference between the different devices. But each of these methods has kind of their own benefits. These are very similar, but typically for a established corporation, they're going to be using one of these two devices for a standard test because they can be calibrated. They're very standard. Their accuracy is very high. They're very specific. But the LCR meter, I'll be showing that too today. And the oscilloscope are complete legitimate measurements. You measure voltage, you measure current, you have impedance. It's as simple as that. It's not something magical that the device does, although there's different methods to get very accurate measurements. That's actually true. So how about we go ahead and we just quickly go over, and this is like a custom software that I built for my my clients that I serve. So today, let's go ahead and do something very familiar to probably most of us here are into power transducers. So let's go ahead and measure this power transducer here. And I have kind of a USB oscilloscope with a voltage probe, and it also has a ground side resistor. And it looks like I have a picture of it. It looks like this basically. There's no amplifier today, but this is a USB oscilloscope. It has a function generator. It measures voltage. It measures current via a ground side resistor. Voltage over a resistor is the current, so we can tell the current in that branch of the transducer. Therefore, I can calculate the impedance using a custom LabVIEW program, taking this data, providing Fourier transforms to get really accurate measurements. And there we go. Therefore, I have impedance, and that's all it is. So you can practically build that, but you won't have the accuracy. And that really annoyed me for a long time of trying to get the highest accuracy and, measuring really high phase angles and low phase angles and really high impedances aren't possible, but you can do what you need to for ultrasonic transducers. That's true. So here's Mr. Transducer here, and I'm going to be hooking it up to these leads. I can explain more about my device, but how I'm measuring it and what the principles are, but that's not the topic of today. Now I'll be trying to attach these leads, which don't really like to be attached to this, but there we go. The leads are attached and we are ready to measure, and just kind of pay attention about what I'm doing when I'm analyzing the device. If you do it like me, then you'll hopefully do it with somebody. You'll be doing it at least close to somebody who has a lot of experience in the area. So let's keep going. So I have 1,000 hertz and 100,000 hertz. And I'm going to be doing a kind of a frequency sweep with 100 and 100 hertz increments. And I think you all should be seeing my screen or generally. Yeah, okay. So this is the transducer. So let's just give it a name. I don't know. This is US cleaner. This is US cleaner. Ultrasonic cleaning transducer. Oh boy, it's not working right now. Hold on. All right. It should be good. If it don't work, then that's not going to be fun. Let me just exit out. It just was working a second ago. Sorry about that. Let me just plug the transducer in. It actually was on. I hope it's not too many things plugged in. I have like 10 USB ports in right now. Okay. Okay. Whew. I was thinking about doing it offline, but I didn't. No, anyway, so let's just go. And what you're seeing here in the blue is impedance, and the red is phase. You can see the phase is close to -90, which is what you would expect for a capacitor. But as the frequency is increasing, so it's sweeping frequency. It's going from 30. Right now it's at 30 kilohertz, as you can see, and now we're going to get to 40. So what I usually do for measurements for transducers, it's valuable to get a large frequency sweep starting out, just so you can understand if there are how many resonances there are. Usually there's only one resonance that's really important to you, but the other ones do tell you information about different parts of the structure, because we know different parts of the structure resonate at different frequencies. Not all of it's important for your actual application, but it is important to know because they can tell you where certain parts are broken. Like if we have this frequency at around 50 or 48 kilohertz, that may represent a certain resonance of the structure, which is sensitive to a certain interface. Now we have issues with our main resonance. We'll also have issues with maybe another particular mode, or may not have issues with that mode, which tells us that interface is actually intact and there's nothing wrong with that part. This is especially important with bolt resonances, which usually we try to definitely design them away from our operating resonance, but they also tell you what the mechanical properties of the bolts are as they are screwed in to the back mass and the front mass there, or the horn. So first we just do a frequency sweep. All right, great. That's great, and we know this is a 40 kilohertz transducer. This part right here, and I'll just we'll just do like a print screen there, just to I think we may only get through this transducer, but that's cool. So this is the response. The resonance frequency is at 40 kilohertz, and I'll just kind of zoom into that area. If you have questions as I'm going, like just curiosities as why there are so many modes, or why there are no modes under this frequency, like this seems clean. Why is that? Or just clean or not non-eventful. So let's go to 39 kilohertz. And let's go to 41. Okay, now it's too, we're not seeing much here. Now 42. Okay, this is a 44. Okay, so you immediately see 100 hertz is not enough because you need several points around the maximum and minimum. All right. So I noticed sometimes when people do take these measurements that they don't use enough points. I see something in the chat. So are the rest, so there's two questions here. Are the rest unwanted measurements? We saw many resonant frequencies. Are these unwanted? You know, they're not unwanted, but they're going to exist because this is a real resonator, a continuous system. So there's going to be multiple resonant frequencies. That's just part of what it is. It's not a single dimensional system. So it's a continuous system. So mechanical system. So there will be other resonances, but we don't want them close. As long as they're far, they can do their thing, you know. You know, so that's basically what we say about the other resonances, but they're insignificant as long as they're not close to the actual resonant frequency. The other question was, I noticed you use a picoscope as your 2-channel oscilloscope. Can you do frequency tracking with this? Yes, you'd be able to do frequency tracking. Now there's certain limitations on this picoscope, and I've run into those. I've tried something similar to this. And I can, but yes, you can actually do frequency tracking with this, with the generator, and you have to have an amplifier, obviously, because the output is 2 volts coming out of the picoscope. So you can use it but there's some challenges that I ran into. So I'll let you run into those challenges too, if you try to do it. That's all I'll say. For other resonances, how close is too close? I guess as an engineer, you get to decide that. Because sometimes the unwanted resonances are bending modes, and bending modes have huge amplitude. And even if you're far off resonance from a bending mode, you still may be affecting your longitudinal mode. So that's kind of up to the engineer to decide that. Maybe you might say 1,000 hertz or something like that. Probably if you're in 2,000 to 3,000 hertz, that's like not a big deal. Also, if it doesn't show up experimentally, but you see it in modal analysis, then you don't have to worry about it per se as much. But that's kind of what I have to say there. So jumping back here, and so sorry I'm talking a little bit fast. This is just a lot to explain here. So you see there's not enough points. So you got to take enough points. What's enough points? Well, enough points is that you have good resolution when you're measuring your quality factor. I'm sure many of you are familiar with the quality factor, but I will actually do that calculation live as well. So let's do 5 hertz. This is going to take longer, but it's going to be, but I'm using a shorter span. No, this is taking too long for a webinar, so I'll put it as 10, and we'll just go ahead with it. So you see the phase starts from -66. If we went further left in frequency, we would have this is here. So it doesn't auto scale by itself, but there seems to be a little bit something funky with this measurement right now. But I'm not gonna dig into that too much right now. Yeah, this is in LabVIEW, right? So this should be a little more sharp, as you are aware. I wonder why it's not doing that today. Why it's kind of acting a little bit stranger today. I think I may be having it hooked up backward or something. Oh, whoops. The connections are a little bit loose. Okay. I'll just keep going here. So there's a little bit of an error, but I will just continue to explain. So this is the anti-resonance frequency. I'll just print screen and I can draw on the other one. So this is the resonant frequency right here of the lowest impedance, and this is the anti-resonance frequency here of the highest impedance. So that's usually 2 things that we end up marking down. So we end up marking the resonance frequency and the anti-resonance frequency. Now I'll just kind of admit I run into this issue sometimes with this program, that it doesn't properly capture the resonant point, or it doesn't create a sharp peak. But we'll just assume for now that this is correct. That this, although it should be much more sharp for an ultrasonic transducer, I'm just wondering why it's not working as it should. I think things are loose in the connection, which is kind of unfortunate, but we'll continue. So there's the resonance frequency here, and also the anti-resonance frequency here. So what other points do we usually go ahead and measure are the resonance impedance and the anti-resonance impedance. And hopefully, okay. Yeah, sorry about that. Usually doesn't, I did notice that noise coming in on my side, sorry. Okay. I'll just try to put it, directly into the computer. If I have a port. Yeah, that should be, hopefully that would be good. Okay. Let me exit out the program. Sorry about that. This usually hasn't happened. Let me see, there's another comment. Yeah, okay. Okay, hopefully I'll stay still, won't touch any cables, and we'll be okay for the rest of the day. So we'll just draw that again, or not draw it, but we'll measure the resonance. So I think there was like some noise or something. So now it appears to be correct in terms of how sharp the frequency is. Because there's an automatic Q calculator. And again, now this is another important point. You should know what your property should be before you start measuring around what properties. So that is also as I kind of showed by demonstration, an important factor. So how do you measure the quality factor? That is something that we know two ways. I want to explain. There's two ways that we usually that one way that's common, and a second way that's very important, but is not as common, but it's based on the same principles. So the first way that's very common is that we look around the resonant point. So we see that this resonance impedance is and let me just reset these scales here to this positive Z phase. So the resonance impedance is 30 ohms. So 30 ohms is the resonance impedance. And then we have, we look around the resonance impedance, it's called a 3 dB up. So you do the resonance impedance multiplied the square root of 2. That's 3 dB higher. So the frequency for this, the frequency of resonance is 39.870 kilohertz. So 39.870. And the frequency that it takes to get to 42, and I'll just move this around to get to 42. And this is why you need to have an accurate scale. So you can actually do the calculations. So I moved that cursor around and I found that 39.790. That's the other frequency. And you do, but basically this is all based off of linear theory, like mass spring damper formulas tell you this, that when you have a resonance point, that you go from this bottom frequency, you find that frequency span, you find that distance that would equal this impedance or whatever magnitude you're measuring, that magnitude times a square root of 2. That actually, which is actually turns out to be 3 decibels higher. That's basically just the conversion. But that actually then that frequency difference, so the quality factor, which is a non-dimensional number, is going to be the resonant frequency divided by the bandwidth. And I think we're all pretty familiar with this method to calculate the quality factor. And that in this case, as it's shown in the program, which does calculate it by itself, it's 234. So we then calculate, so this number here is 234 for this specific transducer. And there's also a quality factor that you can calculate for anti-resonance as well. Certain things about anti-resonance, that it has low current. So there's if you have a lot of wires or resistance and solder connections, they won't be susceptible to the anti-resonance. They won't be susceptible to that because it's such a high impedance anyway. One really important point I want to point out, sometimes for a lot of devices, like a lot of bending devices or non-symmetric devices, the resonance frequencies are really, sometimes it has a lot of spurious modes around it. So this is like an expert tip here, that when the resonance frequency has a lot of spurious modes around it, sometimes the anti-resonance frequency doesn't. And in that case, you can use the anti-resonance frequency as a standard for measuring the quality factor. It'll give you a consistent value. Now, it's slightly different in some physicality than what you're measuring at resonance, but it's consistent and it's derived from much of the same properties. So we have a couple of questions here. Is it the same to plot the Q factor from conductance? I'm actually going to get into that. It's really important. And is the quality factor proportional to the coupling coefficient, or are they independent? The quality factor and the coupling coefficient are completely independent from each other. They're from completely different properties. So let's get into that question of conductance, which is also can be called real admittance. So any impedance analyzer can also, or network analyzer can also plot something called conductance, which is which you can say is the real part of the admittance. And you can go online and look up what different representations exist for impedance. So you can you can, instead of impedance, you can do the reciprocal of impedance, which is admittance. So it's showing how much current is flowing versus how much current is being resisted. And that's not typical of what you learn in high school or perhaps undergrad general engineering, electronics and physics course, for example. But conductance or using the real, I don't know, what comes more intuitively for me is using the real part of admittance. That for some reason I'm attracted more to that. But if we transform this, instead of using admittance and impedance, impedance and impedance phase, we use the real part of admittance and we use the real part of impedance, we get a plot that looks like this. Let's turn off this logarithmic view. So now this is something people haven't seen before. How many people have seen a plot like this? Can you write in the chat? I'm just curious. How many people have seen this? Resistance. This is a real impedance is resistance, and real admittance is conductance. How many, has anyone seen this? Say yes, or you can say no too. Yeah. So yeah, this is actually the real deal for calculating. Yeah, use it all the time. Yeah, the experts use it all the time. so now everybody's expert. So that's why I'm mentioning this. And it's for for ultrasonic cleaners and like high Q devices and high coupling devices, there's no need to do this. But if you're going to take away something today, many of you folks work on like low, like maybe higher frequency devices, or you have low coupling factor, low quality factor. This is like absolutely vital to use for low quality factor, low coupling factor. So I'll just write these notes here. What I'm basically doing. So impedance, impedance that's normally represented as impedance in phase, you can convert that to real impedance and real and imaginary impedance, and 1 over impedance, that is admittance, which is denoted as Y. And that can also be put in its real and imaginary components. Now, real admittance, and I won't go into too much theory here, real admittance and real impedance, which is resistance, will then give you a plot like this. So these are only representative of losses that are happening, and that's and for resonance it's completely mechanical, and for anti-resonance it also is just related to the losses that are occurring in the resistive part of the LCR C branch. So and I'll be showing a buzzer soon. This is so important for a buzzer. You cannot calculate quality factor for a buzzer using this plot before, using this plot. No, it'll be, actually this plot is kind of screwy too, but yeah, let's go back. 1, 2, 3, 4, 5. Where was I? Okay, here. So this is something that your impedance analyzer can do. So you want to calculate quality factor and resonance frequency and anti-resonance frequency from this. So this is actually how I actually can allow. So in my frequency, I have resonance method real or absolute. So this is going to be absolute frequency or absolute impedance, sorry. And this is going to be the real components. So using the real components, you can very accurately calculate the resonant frequency. It's super clear what it is, because sometimes it feels like you step one frequency step right to the resonance frequency, like it doesn't even change. If you step one frequency step left, it doesn't change at all. Like it just seems like this flat, like mashed up like thing that you can hardly analyze. And many people just say it's okay, it's useless, it doesn't really tell us much, but it does. So if you put it in this view, you can actually calculate. So once you do this, when using the when using YR for, and it's called something else. That's called, I think it's called G. I forget the script for it, what it's called. I think it's called G. So when using YR for Q factor, use half the max for the bandwidth. And now it's called not 3 dB bandwidth, now it's called half power bandwidth. You use half. So if this is 32 millisiemens, like this is the real, then you go to what? 16, right? You go down to 16. I'm going down, I'm looking for 16. I got it. Here's 16 right there. So that's how you calculate that. So you go off peaks, which is much more intuitive. I find that a lot of people get confused between kind of all these peaks and things, but yeah. So so just understand that this is a huge point, and I can't emphasize enough how it can be. You can kind of get messed up by doing it incorrectly. I'm going to actually go ahead and measure the buzzer because I want to drive this point home, because I want to make sure. Obviously, I can't cover all the details of impedance analysis in this, but I can cover some really important things, and that's for measuring. One thing is for measuring low Q, low coupling factor transducers using the real components is really important. So let's just stick with that. Let's just stick with that. I'll hook this back in. Hopefully my device doesn't disconnect, overuse USB kind of ports. And since this is a buzzer, it'll be noisy at low frequency. So I'll do that same thing. I'll do from 1,000 hertz to 100,000 hertz, and I'll do it in I guess 100 hertz steps. I think that's what I did before. So here, another cool thing about ultrasonic transducers is that if you run them at 1 kilohertz or lower, you should be able to hear them. And that's a good way of knowing if you made all your connections correctly. I'm also going to put this back into what we're normally used to seeing. I personally, I start with analysis with impedance and phase, because I kind of have an intuition about it. But then I go into the real representations. Now this seemed to have disconnected. Did it disconnect? Something happened here. Let's just I'm a bag full of mistakes right now. So let's just stick at 10,000. So as you can see from this is the blue is the impedance. You see a resonant point happening here. And then you see the phase increasing, which we'd expect. Some people have an issue with the phase not reaching 90. Like they think they saw somewhere that the phase starts at -90 and it goes to 90 and it comes back down. And there's like a concept that has to happen. The phase does not get to -90 if the coupling factor is low and if the quality factor is low. It will not get to positive 90 in the inductive part. Now, I hope I'm still not disconnected. I guess this is my luck today. Something about the attachments. Oh, I went simulator. Oops, this is. Oh, there we go. Okay. Or yeah, there was something up with the attachment. Let me try that again. Okay, so there we go. I'm not making a strong case for my program right now. I recognize that. And that's okay with me. So this is the buzzer. I recommend for anyone who doesn't have a buzzer, like go buy one, because they're really inexpensive and they can use them for learning purposes. Now, the reason some of this is so erratic is because, well, it's like shaking on the table. The other point about this is like, you may actually get measurements like this in your laboratory. So you have to think about how to clean them up. One way is to increase your delay time. So we know that the resonant frequency is 4 kilohertz about, or you can hold it. I'm going to be holding it up in the air pretty soon. So let's go ahead and work on that buzzer and how we can get it to measure better. So I'm going to zoom in around the frequency of interest so I can do measurement there. Okay. Oops, that's too much. All right. Yeah, if anyone else saw this, they'd be like, what kind of device is this? but it's like used quite often. So right now I'm just lifting, taking care. I'm like lifting the transducer off of the table, and hopefully nothing disconnects in that process. I expect not. So this is just holding it up in the air. Now it's much better. See, that whole ordeal was just because I was holding it. It was sitting on the ground. It was like shaking, and it was giving probably bad data. So yeah, be careful about how you hold things and put them in the air. There's some live demo about how things can go wrong. If you're having a webinar and you don't hold your transducer properly, it might cause a problem. Now, this is a real prime example of when you want to use it just feels wrong to use the 3dB method here. Like something probably in your heart tells you that this is not right. And yeah, trust your heart always, right? So what to do here? In your impedance analyzer, you would change your function, but here, this is how I change it to real conductance and resistance. That's a lot nicer to measure. What do you guys think? This is a lot better to measure for quality factor and for resonant frequency. So by your quality factor, now you can actually, so this program automatically does the quality factor for you, but you would have an extremely low quality factor if you measured it in the other way, if you measure it with absolute impedance. So you need to use this for resonance frequency determination, because your coupling factor gets messed up when you don't use this for basically another point I just want to mention, without deleting something I already wrote. For low Q, low coupling factor, it's really important to use, real components to calculate frequencies, both frequencies that also the effective coupling factor, as is calculated from anti-resonance and resonance. You won't get reliable, consistent values if you do that, if you do it using absolute, and especially Q factor. So that is the truth there for these measurements. Let me go ahead and answer questions. Yeah. Can you show the calculation from the admittance plot? Yeah, this is perfect. So I'll do that for you. So here for this transducer, we have 3,775. So the frequency is 3,775. And the impedance, the resonance impedance, or the resonance admittance, sorry, YR, that is 1.19 millisiemens. So I can just leave that as 1.19, and I'll just write the unit here just to make it clear. So what do we need to do? We need to do double, 2.38. So what frequency? So this is what frequency will give us 2.38? I'll just start moving this one around. Or yeah, sorry, half, my bad, half. Okay, so 0.9595. So I'm going down. That means all right there. See, this is why you might want more points. You can also interpolate at this point. That's not a problem, but I'm not interpolating today. This is 3676. The frequency is a 3676. So I'll just continue. So this is the I'll just call this F1. This is FR. And I'll just do F2, which is going to have the same admittance, but it'll be on the other side. Sometimes you'll find this not symmetric. Even despite doing these tricks, you'll find them to be not symmetric. Not tricks, but like these advancements in accuracy. 38 point, and this is the same theory that tells you the same reason why 3dB bandwidth works is the same reason why this works, except this works all the time, because 3dB bandwidth can be misconstrued due to the capacitance. Now, the real part of the admittance doesn't have capacitance, doesn't have that like parallel capacitor messing up with the phase and the absolute values. So if you have, for example, if you have a mechanical system and you measure the absolute displacement versus frequency for a given force input, you can calculate the quality factor using 3dB method. But if you're using a mechanical displacement versus with a force input, but you're calculating how much of that force component is in phase, then you can have to use the half power bandwidth. So this also applies completely to mechanical systems, except we're just not used to, many of us aren't used to analyzing mechanical systems because we just have our heads really far into impedance analysis because it's so easily measured. That's one reason why impedance analysis is used. It's so easy to measure and you get so much information from it. So going to the other side, this is 3841. So just to complete the measurement, so I have the resonance frequency divided by the half power bandwidth, which is this number minus this one, 22, and my program uses the same calculations, I get 23. So that's good. And also keep note that my anti-resonance frequency is here. It's at this peak of resistance. Now I want to just go back and show you what it looks like if you plot this. So you'll notice that the impedance value for this is not too bad, I'll be honest, because the anti-resonance frequency is kind of still near the maximum impedance in blue, and the resonance frequency is not at the minimum point. It's not here. This is the minimum impedance, but the resonance frequency, which is in my program calculated according to this factor, is not there. Now I want to do another thing. So you'll get but you absolutely cannot calculate Q using this. This would be a terrible idea. It's so flat. It's like you keep gonna go, like you start here. This is 70. This is like 700 ohms, and if you go, in order to get double 700 ohms, you have to be like completely out of the resonance area. It would be obvious that you're doing something's going on here. I want to do something else. I want to end with this. I had a couple of things I could have talked about. I was going to talk about capacitance, but I'm going to hold this, and we all know what's going to happen when I hold this. The response is going to die down. So I'm holding the transducer. And I think I just eliminated the resonance, which is not what I wanted to do. I'll just do that. I don't think I want to hold it lightly. I don't want to completely eliminate it. So sometimes, like this buzzer here, it's not meant to just sit in air and be tested. You want to glue it, or whatever transducer you want to have, you put it in a different environment, and it is very useful to analyze your transducer there. I won't go ahead and do a finer measurement, but just to drive the point home here about now the resonance and anti-resonance frequency, they're not much closer. I think their frequency did shift. So let's do 3000. Let's do 4200. I'm about to finish here, guys. Just letting you know. And I'll just run this again, lightly holding the transducer. So that looks really nice to measure. I don't know about you guys. Like to analyze the quality factors of resonance and anti-resonance, and also to pick out where the frequencies are. Now we go to the other side, and it becomes a lot harder. Look how far the resonance frequency, both the anti-resonance frequency and the resonance frequency are not at the peaks. All right. So you would actually be doing a terrible calculation. You'd be calculating a higher coupling factor, and you'd have your coupling factor actually now affected by the quality factor. It would be an incorrect measurement to do because of that reason, and you would have the wrong coupling factors calculated. And when you're trying to analyze, especially this happens in FEA, when you're trying to correlate data, you're trying to correlate your your mechanical and your electrical data, and you're trying to make sense of what to input for parameters, you have to be measuring things correctly. And I think I'll end with that. A couple of the things I was also going to share, but I think there's not enough time today, is the importance of LCR meter measurements. That is very important for capacitance and dielectric loss. That's something that's often overlooked. But today we mainly went over using the real part, basically conductance and resistance. And I think that pretty much, and I basically showed you the Langevin transducer, and also the unimorph morph / bending, which was also, it's a good example of a low Q, low coupling factor device. And I will stop the recording